Hello, everyone. My name is Antonio Coleman, and I would like to welcome you to the newest installment of my ongoing series where I cover various topics in computer organization and architecture. Before we begin, if you have not seen my previous video where I explored how to convert radix bases, I would highly encourage you to do so. But nonetheless, let's begin this video. But first, let me explain the concept that I will be covering. This video's target focus relies heavily on central processing units, commonly related to CPU, along with memory hierarchy. First, we will be covering what a CPU or central processing unit is. For reference, by now, if you're familiar with computer systems at all, you've likely heard the comparison of processors to the brain for computer systems. And this is done for good reasoning. This is because every action that is performed on the device, whether it be moving your mouse or playing a video on YouTube, for example, these both require millions of rapid-fire calculations. As this happens, the CPU in specific is the primary component responsible for both processing as well as executing all of these instructions. Now let's explain the function of the control unit, or CU. To begin, since we referred to the CPU already as the brain of the computer, you can think of the control unit as the central nervous system for computers. It doesn't actually perform any of the mathematical calculations or process the data itself. Rather, it directs the operation of the entire CPU. This is done by the CU both reading and interpreting the instructions that are fetched from your computer's memory. Here, the CU generates the precise timing as well as the control signals that are needed to tell the arithmetic logic unit, also known as the ALU, the memory, and all other connected input and output devices exactly what to do and when to do it. Now that we just briefly referenced the ALU, it's time to focus on what the arithmetic logic actually does. Here, the arithmetic logic unit acts as the specialized worker, which rolls up its sleeves to do all the heavy lifting. This is the section of the CPU where all raw data processing takes place. Here, it handles two specific tasks: arithmetic operations, which include basic math like addition, subtraction, multiplication, and division, and also logical operations. These logical operations include making comparisons and decisions. Examples of this include determining if one value is equal to another or evaluating true and false conditions. Now we can discuss the concept of instruction pipelining and also its advantages in enhancing CPU performance. Let's first begin by describing a standard non-pipeline CPU and its processes. This process initiates as the processor fetches, decodes, and executes a single instruction completely before it even looks at the next one. The con here is that this is highly inefficient because it leaves parts of the processor sitting idle. For example, while the ALU is busy executing an instruction, the fetching unit is just waiting around doing nothing. However, pipelining solves this by overlapping these stages so that multiple instructions can be processed simultaneously. This begins as soon as the first instruction moves from the fetch stage to the decode stage. This is important because the fetch unit immediately grabs the second instruction, allowing for the CPU to constantly remain busy at every part rather than a bottleneck. Now it's time for us to move on to memory hierarchy. Here we have levels which include registers, cache memory, main memory, or RAM, and also secondary storages like hard drives, USBs, and also SSDs, which stands for solid state drives. At the very top, we have registers, which are tiny storage locations inside the CPU itself. It's important to note that they are the fastest memory in the entire system, but can only hold a few bits of data at a given time. When we look below that level, we find cache memory. This includes L1, L2, and also L3. It is important to note that these are essentially teammates for the CPU, which work to help catch things the CPU may miss and also provide instant access to critical data. Now, as we continue to move down, we see main memory, or RAM, which is known as random access memory. This is by far larger than the cache memory and works to store the apps and data that you are currently using. However, it's volatile, which means that it wipes clean when the power goes out. Now, at the base of the hierarchy, we find secondary storage. This includes things like USB, SSD, and hard drive. This is where your files live permanently. Additionally, they offer massive capacity and are very inexpensive per gigabyte. But compared to the lightning-fast registers at the top, it is significantly slower to access. And now that we have covered concepts in both the central processing unit as well as memory hierarchy, we have come to the conclusion of this video. I hope you enjoyed. Feel free to like and subscribe as well so that you can come back for more videos like this. Thank you.